It is evening in Babylon. The river is the color of bronze. On the roof of a brick ziggurat, a priest counts the stars. He does not know it yet, but the marks he is pressing into wet clay tonight will still be ticking 4,000 years from now on the wrist of every human being alive. This is the story of the strangest thing we ever built. Not a wheel, not a wall, not a fire. A second. Look at your hand. There are 12 joints on the 4 fingers, if you count from the base. Press your thumb to each one in turn. 1, 2, 3. By the time you reach the smallest joint of your little finger, you have counted to 12. Now use the other hand to keep score. Each time you finish a cycle of 12, raise 1 finger. 5 fingers, 5 cycles. 12 times 5, 60. This may be how it began, 5,000 years ago. In a city of mud, brick, and reed, on a flat plain between 2 rivers, a Sumerian scribe pressed a wedge into wet clay and counted to 60. And then she counted to 60 again, and again. She did not invent time. Time was already there, in the rising of the sun, in the swelling of the river, in the slow march of the stars across the night. What she invented was a way to cut it. The Sumerians and the Babylonians who came after them built a number system on the base of 60. Not 10 like ours, 60. And they had their reasons. 60 is a generous number. It can be divided cleanly by 2, by 3, by 4, by 5, by 6, by 10, by 12, by 15, by 20, by 30. Try that with the number 10, and you will quickly run out of clean answers. 60 was a number you could share, a number you could split among farmers and merchants and priests without anyone feeling cheated. So they built their world on it. 60 grains in a measure, 60 measures in a sack, 60 degrees in the angle of an equilateral triangle, 360 days in a year, 6 times 60, 360 degrees in a circle. And when the moon and the sun crossed the sky, the Babylonians cut their motion the same way, into 60 parts, and then 60 smaller parts inside each one of those. 5,000 years later, when you glance at the clock on your phone, 11:47:23, you are reading a Babylonian sentence. The hour, 60 minutes long. The minute, 60 seconds long. The pilot's compass, 360 degrees around. Latitude, longitude, the geometry of every map. All of it, a Sumerian inheritance. No other Bronze Age invention has survived so completely. The Sumerian language is dead. Their cities are dust. Their gods are forgotten. But their arithmetic is still on your wrist. Now, why 24? Why does the day, of all things, refuse to obey base 60? For that, we have to go further west, to the banks of the Nile. In ancient Egypt, the priests were not counting fingers, they were counting stars. They had identified 36 small constellations, they called them deacons, that rose one after another through the long Egyptian night. 12 of them were visible between sunset and sunrise, 12 hours of darkness. By daylight, the sundial gave them 10 more. Add an hour for dawn, add an hour for dusk, 12. 12 and 12, 24. That is the answer. The day on your watch is not Babylonian. It is Egyptian. And it was never about mathematics. It was about which stars were visible above the desert 4,000 years ago. But there is something strange about those Egyptian hours. Something almost no one remembers anymore. They were not the same length. A summer hour in July, when the sun lingered, could stretch to 75 modern minutes. A winter hour in December could shrink to 45. For nearly all of human history, for thousands of years, across nearly every civilization on Earth, an hour was a fraction of daylight. It expanded and contracted with the seasons. It belonged to the sun. Time was something the world did to you. It would take a very strange invention to change that. A machine that did not know what season it was. A machine that did not care. A machine that simply ticked. It is 4 a.m. in a Benedictine monastery, somewhere in the cold heart of medieval France. A monk is climbing the bell tower. He climbs in the dark. He has been climbing this same staircase at this same hour for 30 years. In his world, time is prayer. 7 times a day and once at night, the brothers must gather to chant. Matins, lauds, prime, terce, sext, none, vespers, compline. 8 punctuations on the long arc of devotion. But how do you wake 40 sleeping men in winter before dawn? How do you do it at exactly the right hour every day for 1,000 years? The answer, when it came, was made of iron and weights and falling things. Sometime around the year 1300, in monasteries scattered across Europe, a new kind of machine began to appear. A wheel, a weight on a rope, an escapement, a small, clever mechanism that let the weight fall not all at once, but in tiny, regular jerks. Tick, tick, tick. It had no face, it had no hands. It had only a hammer and a bell. The word we use for it, clock, comes from the Latin clocca. It means bell. For decades, in every village and every town, the people of Europe did not see time pass. They heard it. The cathedral bell tolled the hour, and the world stopped what it was doing and listened. The Salisbury Cathedral clock, in the south of England, was built around 1386. It has no face, just gears and bells. It has been ticking, more or less continuously, for over 600 years. By one estimate, it has tolled the hour more than 500 million times. The historian Lewis Mumford once said something about that machine. He said the clock, not the steam engine, was the key invention of the modern age. Because the clock was the first machine that broke time away from human events. A medieval plowman did not work for an hour. He worked until a job was done. A merchant did not meet at 10 o'clock. He met at the bell. But once the bell could tick on its own, indifferent to the sun, indifferent to weather, indifferent to whether anyone was even listening, once the clock did not need a human to keep going, then time became a thing in itself. Something that did not flow, something that passed. And once it could be measured, it could be sold. Now, the bell in the monastery is one thing, but what about a bell at sea? Picture a wooden ship, the middle of the Atlantic, 3 months out from England. The captain knows, from the sun at noon, exactly how far north or south he has sailed. That is latitude, and any decent navigator can read it. But how far east or west? That is longitude, and in the year 1700, no one alive could answer that question with any certainty. The principle was simple enough. The Earth turns. Every hour it turns 15 degrees. So if a sailor knew what time it was at home, at say Greenwich, England, and what time it was where his ship now floated, he could subtract one from the other and know his position to the mile. The principle was simple. The problem was the clock. Every pendulum clock that worked on land became useless at sea. The roll of the waves, the swing of the deck, the temperature, the salt, the damp. No clock ever built could survive a year of ocean. In October of 1707, 4 British warships, returning home through the fog, miscalculated their position by a few degrees of longitude. They struck the rocks off the Scilly Isles. Nearly 2,000 sailors drowned in a single night. 7 years later, the British Parliament offered a prize, £20,000, several million in today's money, to anyone who could solve the longitude problem. It was the largest scientific bounty in human history. A man heard about it. A carpenter's son, from a small village in Yorkshire. He had no university degree. He had never been to sea. His name was John Harrison, and he was 37 years old. He would spend the next 46 years of his life building a clock. His first attempt, H1, was finished in 1735. It was a brass machine the size of a small wardrobe, 75 pounds of gears and counterweights. It went to sea, and it kept time. The Board of Longitude was impressed. They gave him a little money. They asked him to keep working. So he did. H2 took 5 years. H3 took 19. 19 years on a single clock. Along the way, he invented 2 things you have probably never heard of, but that are still, to this day, in almost every machine on Earth. The bimetallic strip, which lives inside every thermostat, and the caged roller bearing, which lives inside almost every engine. But H3 still wasn't accurate enough. Harrison was 62 years old. And then, sometime in the early 1750s, he had an idea so strange that almost no one believed it could work. What if the clock got smaller? What if, instead of a wardrobe, it could fit in a pocket? H4 was completed in 1759. It looked like a fat silver pocket watch, 5 inches across. Inside it, a tiny balance wheel ticking 5 times a second, with diamond pallets in the escapement and a temperature-compensated spring. It was beautiful. In 1761, Harrison's son William boarded a ship in Portsmouth and sailed to Jamaica with H4 wrapped in cloth. 81 days at sea, storms, heat, ice. When the ship made landfall, the clock had lost 5 seconds. To win the prize, the watch needed to keep its position to within 30 miles. H4 was accurate to within 1. The Board of Longitude refused to pay. They demanded a second trial. They got one. Harrison passed it. They demanded a third, then a fourth. They asked him to disassemble H4 in front of a committee and explain every part. He did. They asked for the full plans in writing. He gave them. They asked for copies to be made. He waited. Years passed. Harrison was now in his late 70s, tired, half blind, convinced he would die unrewarded. In 1772, his son sent a 5th clock, H5, to be tested by the king himself. George III placed the watch on a shelf in his private observatory at Kew. He watched it tick for 10 weeks. It lost 1/3 of a second per day. The king is said to have stood up, looked William Harrison in the eye, and said, "By God, Harrison, I will see you righted." In 1773, Parliament released the final payment. John Harrison was 80 years old. He died 3 years later. Out at sea, on Captain Cook's second voyage of discovery, an exact copy of H4 was already crossing the Pacific. Cook would later write of that small, ticking watch, "Our faithful guide through all the vicissitudes of climates." It mapped Australia. It mapped the Polynesian islands. It threaded 1,000 ships through fog and storm and brought them home alive. A Yorkshire carpenter's son, in his small wooden workshop, had given the British Empire its sense of direction. And the clock kept ticking. A century passed. Harrison's chronometers became smaller, cheaper, more accurate. By 1815, there were 5,000 of them at sea. The world's ships found their longitude. The world's maps grew honest. But on land, time was still a local affair. In 1870, if you walked from Toronto to Montreal, you would pass through a dozen different times. Each town set its clocks by the sun directly overhead at noon. Toronto noon was not Montreal noon. Boston noon was not New York noon. There were, by one count, more than 140 different local times in North America. The railroads alone ran on more than 80. The wall of any major train station carried not one clock, but 3 or 4 or 5, each one set to the time of a different railway company. Travelers stood beneath them, baffled. Trains running on shared track, in shared time confusion, sometimes met each other head-on. It is July of 1876. A Canadian engineer, Scottish-born, named Sandford Fleming, is standing on a small railway platform in the town of Bern in the west of Ireland. It is a bright summer afternoon. He has arrived early. He is going to Londonderry. The schedule, printed clearly in his pocket, says 5:35 p.m. 5:35 comes. 5:35 goes. The platform is empty. He goes to the station master. The station master shrugs. "The 5:35, he says, is a morning train. 5:35 a.m. The schedule was misprinted. Sandford Fleming will spend the next 16 hours on a wooden bench in the rain in a country not his own. And in those 16 hours, he will conceive of an idea that will change how every human being on earth keeps time. There would be no more AM and PM. The day would be 24 hours long, numbered straight through, midnight to midnight. No confusion possible. And there would be no more local time. The earth would be cut, like the Babylonians cut the circle, into 24 equal slices, 15 degrees of longitude each, 1 hour each. Anchored to a single meridian, Fleming first proposed an imaginary one at the center of the earth that all the world could agree on. He called it, beautifully, cosmic time. In November of 1883, the railroads of North America, working from Fleming's design, synchronized their clocks. On that day, known to historians as the Day of Two Noons, many cities saw their clocks jump backward or forward by minutes. Sun noon happened, and then, a little later, clock noon happened. It was the moment time stopped belonging to the place you were standing and started belonging to a global agreement. A year later, in October of 1884, 25 nations met in Washington, D.C. for the International Meridian Conference. They voted on a single prime meridian for the world. Greenwich, England won by 22 votes to 1. France abstained in protest. For the first time in human history, every clock on Earth could be set to the same beat. One Earth, one time. A man missed a train and rebuilt the world. We had counted the stars. We had counted the bells. We had counted the swing of pendulums and the spinning of balance wheels. But by the middle of the 20th century, all of these were too slow, too imprecise, too earthly. In a quiet laboratory in Teddington, England, in June of 1955, a physicist named Louis Essen turned on a strange machine. It looked like a metal cylinder draped in wires. The engineers nicknamed it the Flying Bedstead. Inside, a beam of cesium atoms, atoms of a soft silver metal called cesium-133, was being asked a single, very narrow question. At what frequency do you vibrate? The answer, when it came, was a number so precise it almost frightened the people who measured it. 9,192,631,770. 9,192,631,770 oscillations of a cesium atom. That, by international agreement signed in 1967, is 1 second. Not the swing of a pendulum, not the rotation of the Earth, not the orbit of the planet around the sun. An atom. For the first time in 5,000 years, the second on your watch was no longer tied to anything in the sky. The Earth itself had been quietly demoted. Its rotation was no longer the standard. The atom was sovereign. And the atom was almost perfect. Today's best atomic clocks would not gain or lose a second over the entire age of the universe. But here is where the story takes its strangest turn. In 1905, a 26-year-old patent clerk in Bern, Switzerland, surrounded by drawings of railway clocks and telegraph synchronizers, wrote down a sentence that should have been impossible. He wrote that time is not the same everywhere. He wrote that a clock moving fast ticks slower than a clock standing still. He wrote that a clock high on a mountain where gravity is weaker ticks faster than a clock at sea level. His name was Albert Einstein. For 60 years, almost no one could test it. The differences were too small. The clocks weren't good enough. Then, in October of 1971, two physicists named Haffler and Keating did something almost absurd. They bought commercial airline tickets, not for themselves alone, for 4 cesium atomic clocks. They flew them around the world, east, then west, then home. When they landed and compared their flying clocks to the master clocks at the US Naval Observatory, the flying clocks disagreed. By exactly the amount Einstein had predicted more than half a century earlier. Time really does flow differently for things that move. time really does bend in gravity. The patent clerk had been right. And every single time you ask your phone for directions, you are using his equations. Right now, 20,000 kilometers above your head, a fleet of GPS satellites is orbiting the Earth. Each one carries an atomic clock. Each one is moving at 14,000 kilometers an hour, in a region of slightly weaker gravity than the surface where you stand. Special relativity says those satellite clocks should run slow, by about 7 millionths of a second per day. General relativity says the weaker gravity should make them run fast, by about 45 millionths of a second per day. The net result: every GPS clock above you is ticking 38 microseconds per day faster than your watch. It does not sound like much, but it is enough that, without correction, the blue dot on your map would drift wrong by 10 kilometers a day. The system would be useless within minutes. So the engineers do something elegant. Before each satellite is launched, they deliberately slow its clock down. They tune it to tick at a frequency just slightly below normal, so that when it reaches orbit and Einstein's equations take over, it ticks back up to match the Earth. Every satellite carries a clock that lies on the ground in order to tell the truth in space. The blue dot on your phone is a 100-year-old equation, working in real time. 1600 years ago, a man in North Africa sat down to write his memoirs. His name was Augustine, and at one point in the 11th book of his Confessions, he stopped and asked himself a question. What, then, is time? He answered, in the next sentence, with one of the most honest things ever written. If no one asks me, I know. If I wish to explain it to him who asks, I do not know. We have spent 5,000 years building instruments to measure something we still cannot define. The Sumerians cut it into 60 parts. The Egyptians divided it by the stars. The monks tolled it on bronze bells. Harrison chased it across the ocean. Fleming negotiated it across the world. Einstein bent it into geometry. The atom subdivided it into 9 billion pieces. And still, when we sit alone in a quiet room and try to hold what time is in our hands, it slips away. Augustine had an answer. He thought time exists only inside us, as memory of what was, as attention to what is, as expectation of what is to come. 3 motions of the mind woven together. He called it distentio animi, the stretching of the soul. The Italian physicist Carlo Rovelli, writing in our own century, has come to a stranger conclusion. At the deepest levels of physics, at the scale of the smallest grains of space, in the equations that govern the universe at its most fundamental, time disappears. The variable is not there. The fundamental equations of reality have no need for it. It may be that the great river we have been measuring all along, the river of past and present and future, exists only at our scale, only for creatures like us. Time may be the way the universe feels when it is being us. We did not discover time. We are still inventing it. Knuckle by knuckle, bell by bell, atom by atom. And yet, the watch on your wrist is keeping a Sumerian rhythm older than the pyramids. The hour you are inside of was named on a temple roof in Egypt. The minute you have just spent was told, in some sense, by a monk you will never meet, climbing a stone staircase in the dark. The second you are spending now was approved by 25 nations in Washington in 1884 and locked in 1967 to the vibration of an atom. 5,000 years of human striving, all of it ticking against your pulse. That is not nothing. That is, quietly, against all odds, a kind of song. So the next time you glance at the clock, on your wrist, on your wall, on your phone, and you see the small numbers march forward, 11:47:23, 11:47:24, 11:47:25. Remember, each of those seconds was negotiated by scribes and priests and monks and carpenters and engineers and physicists, by people who lived their whole lives and never saw the answer. The clock is a human invention. The hour is a human agreement. But the moment, when it finds you, is the only piece of time that was ever yours to keep. This is Cosmic Canvas, where we find the human story inside the cosmic one. Until next time, remember that you do not pass through time. Time is the medium of your becoming.